Data Analysis Part 2. Describing Data, Descriptive Statistics, Important Principles, Examples and Hazards of Data Visualization. Hello everyone, welcome to Part 2 of the Data Analysis videos for the MPhil ACE in Chemical Engineering and Biotechnology. In this video I want to go through Chapter 2 of the course notes on describing data. Let me start by trying to explain the title picture I've used for this video, which I captured from the internet in the sweltering hot summer of 2015 when I was sitting around in the office watching Test Match Special on the BBC's live stream, and everybody else was off on their summer holidays, so they didn't mind me sitting around occasionally grabbing quotes that I was amused by. So this is a conversation. For you, if you don't watch Test Match Special, it's partly a radio commentary on important cricket matches. This one was England-India, but a good half of Test Match Special is actually just the somewhat elderly commentators talking about whatever's passing through their heads, and they occasionally the BBC's commentators would ask their volunteer statistician seemingly impossible questions, just for amusement, to see if he could come up with statistics that you couldn't possibly know. So I think it was Andrew Boycott, or it could have been Blowers, demanded of Andrew Sampson, the volunteer statistician. They observed that in this particular test match, it was pretty unusual in their experience, because the Indian captain Mahendra Singh Dhoni was changing his bowlers very frequently, and someone asked the statistician, I think Dhoni's rotated his bowlers every single over since lunch. Is that the most bowling changes there have ever been in a session of Test match cricket, Andrew? Andrew Sampson replied, "This is an impossible thing to know off the top of your head, by the way. I don't know, but if you give me a few minutes, I can find out for you." What's the point of this story? He duly did find out the correct answer in about 10 minutes, and the answer was that no, there were about 4 test matches from the last 50 years or so which were tied or had more bowling changes in a session than the one they'd been watching. Why is this important? Because I want to point out that although in the first lecture I said statistics is the science of handling data, and it splits into 2 parts, descriptive statistics, where there's no uncertainty in the conclusion that you're drawing from data, and inferential statistics, where we're drawing fundamentally uncertain conclusions. Although it's very important to distinguish these, and inferential statistics is the hard topic which you'll probably need to do in science, actually you can get good money, you can get good kudos and accolades, and be very well respected purely for being able to do descriptive statistics. In other words, purely for being able to record data in a comprehensive way that can be efficiently searched by a computer system, and that's what Andrew Sampson actually is famous for. You can get an award from appreciative members of the public who are happy simply that you've tabulated data correctly, recorded it, and you can very quickly write a computer script in R or something else, go through it, and pull out tidbits of trivia which amuse people, or they could even be important, say, for example, to settle a bet, or for some more serious reasons. So, descriptive statistics is important, and it's the building block for doing advanced analysis, but it can be useful purely on its own. Let me look at that point in a bit more detail. I think there's actually 2 very important ways that purely doing descriptive statistics, or accurately describing some data that you've collected, there are 2 reasons why this can give you huge benefits without needing to do any kind of sophisticated mathematical analysis. So, Reason number one is that sometimes when all you do is simply produce a graph which illustrates the data you've collected, sometimes it makes some conclusions absolutely obvious without needing to do a further mathematical analysis. The conclusion just stands out. You could, for example, look at statistics on life expectancy of lifelong smokers from a country compared to non-smokers from the same country. The difference would be very clear. There are hazards in looking at this because there can be confounding variables. We'll talk about these later in the course. There are dangers in just interpreting a graph without either a sophisticated mathematical analysis or without thinking in depth about the topic, but sometimes you only need to describe your data that you've collected. You only need to produce an accurate graph, and the result is pretty clear for all to see. That's one reason. The second reason I think descriptive statistics is important is one that I think a data scientist won't admit this to you. But let me briefly describe a topic called quality engineering, which is an important trend in manufacturing industry for the last 50 or 60 years. And let me describe this in the context of the car industry, and in particular the Japanese car industry. So this story, so back in the 1970s, a British car company, some technicians were asked by the management, why are we losing market share to Japan? And duly they bought a Japanese car, had it delivered to the factory in Britain, and the technicians opened it up, and they were horrified by the high quality, the almost science fiction high quality of the engineering that had been done under the hood of this Japanese car. It was of substantially higher build quality than anything that was being produced in this factory in Britain at the time. Why is this? Well, Japanese manufacturing industry in the 50s, 60s and 70s, and still today, embraced the concept of quality engineering and continuous process improvement. If you want to learn more about the history of this, or you're considering working in the automotive industry, you should look up the name William Edwards Deming on Wikipedia, or you could look up an industrial standard like Six Sigma, which happens to be important in the car industry. The point is that instead of doing occasional product inspections and non-systematic feedback and improvement of methods, in quality engineering, the Japanese car industry embraced the idea that you can measure and record permanently the properties of, well, first of all, some properties of finished products, but also you can record properties of intermediate components which are not yet the finished item. So you don't just inspect the final product, you also record properties along the way of its production. What is the advantage of this? Well, partly, data scientists might tell you, well, if you record, in making a wheel, if you record the torque which has been applied to each of 12 bolts, then you can later go back and do some analysis, and you can see that for a particular item, the average torque was 1% above the required spec, and the range was such and such, say plus or minus 3% of the absolute value. And you could compare this kind of data against failure data. You could do, in other words, some very complicated data analysis. That's what a data scientist might tell you. Actually, a large part of the benefit of doing total quality and recording data is not particularly that you are able to do sophisticated analysis. It's that if you are obliged to record the torque on each of 12 bolts, you are very unlikely to accidentally only use 11. Essentially, it's the fact that people are forced or assisted to work systematically simply in order to record data comprehensively, that actually gives you a large amount of benefit. The fact that you could then do something sophisticated with the information you've recorded is not necessarily as big as the advantage you get simply from being forced throughout an industry to work systematically, and so that you can record data consistently for each of every component. So that's a side benefit of descriptive statistics. It's simply that setting up, as far as industry is concerned, simply setting up their business to be able to systematically record data makes their working practices better without needing to do anything difficult. This course, of course, is about data analysis, so I mention this because I think it's important, and I'm a physicist, so I can tell you this. A data scientist might not admit that a large part of the benefit of employing data scientists comes from making the business work systematically so that they can employ data scientists, not from anything the data scientist does. Great. So we said two benefits there of descriptive statistics by themselves. Number one, a real benefit that sometimes a good graph or a good description of your data makes a conclusion obvious. Second, simply being able to record data has advantages of its own, even if you don't use it for very much. Of course, a third reason we'll be making use of later in the course, that once we've recorded data, it's the building block for doing more advanced inference and learning from scientific measurements. Right, in the first video of this series we said that statistics is the science of data, and this course was concerned with how we learn from data, whether it's learning from experimental scientific data, learning from data that you read in the news, or interpreting and making improvements using industrial measurement data. We said that there's a difference between descriptive statistics and inferential statistics that I've just been talking about, and that descriptive statistics is sometimes important on its own. In this video, we'll briefly look at some principles that are important in data visualization, some example hazards that will come up for which we need to know the limitations of purely describing data. We'll briefly look at some numerical or mathematical formulae for summarizing data, but I'm going to mainly leave that for something you can read from the lecture notes or from textbooks. We also, in the first lecture, mentioned the Bayesian approach to learning from information, that we're going to be using the principle, what we know after we get some data is what we knew before, plus what the data told us. Right. Chapter 2, Reporting and Summarizing Samples of Data. In order, as we said, to learn from observations or experimental measurements, it is first necessary to describe the data that has been obtained. This chapter is a quick review of the most important principles in presentation of data, especially graphical data, and also some comments on numerical statistics. How is data described? Well, it's actually an art, but you will be familiar that data can be given to you pictorially in the form of bar charts, scatter plots, digital image data. Data can be given to you numerically as a table of measured numbers, or those can be summarized sometimes into a sample mean or a correlation coefficient between some of the measured numbers. Or data can be given to you as a written statement, as in a news report. Very important fact here. So one of the most important mistakes which undergraduate students and master's students make when they are presenting reports, presenting theses and dissertations and things, is they present some data and they have a section results and they put some graphs, and they don't appreciate that the graph they're providing and the caption of the graph, these are both forms of data which they're presenting, and the most common mistake or problem I find with student dissertations is that the captions are nowhere near detailed enough. You've got a graph which sometimes meets all of the high quality standards you'd hope for, but almost all graphs need a detailed caption. So the difference between your undergraduate or graduate students and your good PhD dissertations, theses, is that your good PhD theses and any published papers have much more comprehensive but still compact written captions for all of the figures, so that they actually fully present what the measured results which you need to convey. What's the best way to explain to you how to do this and the right amount of detail to put into the caption for a figure? Well, the right amount of the way to do this is that you imagine that if you're handing in a dissertation, some lazy so-and-so reading it, they read the title, they read the abstract or the summary if it's nicely written and it's not too long. They read a few of the first sentences of the introduction, and then they page through looking for a graph. And assume that when somebody looks at a graph, they'll have read the abstract of your title and abstract, maybe your introduction. But then the next thing they've looked at is the graph and its caption, and you have to pretend that's on a standalone page, and that people have not read any of the text for your, perhaps not even for the methods section, and they haven't read any text describing the experiment, describing the results in your text section of your results chapter. They're just looking at the figure and its caption, and from that they should be able to get a reasonably correct concept of what's what of the data that you're presenting. So, for example, here is a just about good enough example of how to present a graph of some data for a simple experiment. This is a nice little experiment that's been done with the help of some guinea pigs, and you might find in a dissertation this graph. This graph is okay as the graph goes. It's a dot plot. It's got labelled axes, length and dose. We are not given a dimension for length, so that seems like a bad thing. We're not given what the dose 0.51 or 2 means, not in the colour legend, but you can read off the y-axis of the dot plot dose milligrams, and you've got a title, Plot of Length by Dose. And you might find that in a student dissertation, and you might just find figure caption, figure 1, guinea pig results or something, and that would be no good. You could make this, so you've got, however, a lot of numerical data there which has been turned into pictorial form. In practice, what you also need is a caption which contains additional data which completes the business of giving the results. Here's a just about acceptable caption: tooth growth rate. Here, incisor tooth length in millimeters in guinea pigs is shown after a set period of treatment with a daily dose in milligrams per day of vitamin C. So between that caption and the graph, you can see that there's something pretty important going on here to do with vitamin C being needed for guinea pigs to grow properly. That's actually, if we looked at the topic, that's a fairly interesting result. As it happens, let's talk about the biology significance of this. Most animals actually produce their own vitamin C. Guinea pigs, along with humans, don't. So guinea pigs are one of the few other animals, apart from us, that can get scurvy if they're not fed vitamin C in their diet. That's not a problem, naturally, because the natural diet of guinea pigs, like the natural diet of humans a long time ago, includes so much vitamin C that the ability to produce it with your own cells isn't actually conserved by evolution. So guinea pigs like us lost the ability to make vitamin C. This graph shows some actually quite detailed numerical results looking at that fact, and doing so in the sense of, well, their teeth need to grow, and if they don't regrow, they get worn down by the stuff which the nice creatures eat. I won't go through the text of section 2.1 or any of the other sections in detail. 2.1 is on dot plots. I will simply say there are key features of graphs and of captions which you should know about, and which you should discuss with a supervisor, or read up more standard recommendations on report writing if you haven't come across this in the past. But your key features of graphs: legible font size when the thing is rendered onto a page, concise, jargon-free labels, so you see your caption and your concept length and dose in the graphs. These are not weird acronyms that no one's going to know what they are. Those are understandable in plain English. And as I was saying, enough details in the caption to free up the figure from the main text of your dissertation so that it could float on a page of figures with its own caption and still be useful to someone who's just read the title of your dissertation and knows roughly what it's about. You should also have a reference number for all of your figures, so 2.1b in this case. Nice to have features: vector graphics. You can look up more about the difference between vector graphics and scalar graphics. This graph which I've got here is actually partly vector graphics and partly scalar. If you haven't come across what this means, I'll show you on another slide later, or maybe I'll zoom in on it here. No, this one's actually a nasty raster graphic. So I'll show you a vector graphic later. Nice to have: display independent of color. So here we've got red, green, and blue distinguishing different kinds of dose, really for proper accessibility of the figure, or in case someone prints it without color. Those markers should have different shapes, like circle, triangle, square, as well as having different colors. Many graphing packages like ggplot in R and other statistical packages which are available will do the business of using distinct colors and distinct shapes for markers automatically. If you have something like Excel which doesn't necessarily do that, then you should be aware to force it to happen to make sure that you get a good quality picture for your pictorial data in your dissertations. Good. Right, vector graphics and raster graphics, so that you know the difference exists and you can, when possible and convenient, use vector graphics for your dissertations. You have two images on this slide, and if we zoom in on the top version of this graph, you see it becomes blocky. That's because it's a raster image, and the data represented in PowerPoint is a rectangular array of pixels. Each pixel comes up on the screen as a square. When you zoom in, the square has to get bigger in comparison. So if you save as a PNG or a JPEG, you get a raster graphic like that. If you do have the opportunity to save a vector graphic format, like sometimes a EMF, sometimes a PDF, then you can get this zoomed in graphic from the lower figure, so that you see the text, and most of the lines aren't stored as a rectangular array of pixel values for black-white darkness. Instead, they're stored as a description of positions and lines between them, so that your software can zoom in nicely. This means that when you do all kinds of printing, if your graphics program can handle it, and if your printing system can handle it, you get better quality graphics when your figures are vector graphics. Sometimes you get a mixture of the two, so you find that your blobs are sometimes not very nice poor raster graphics, but your graph as a whole, if it's possible to make it as a nice vector graphic, you get a better quality. Right, that's just mentioned that those two things exist, and that if possible, you want to be handling your graphics as EPS, PDF, or EMFs when those are vector format. What else can we say about describing data and graphs in general? A few comments on R and RStudio, which you probably, if you are doing this course, you will probably want to use MATLAB for doing your data processing and producing visualizations. MATLAB is widely available in the universities and in industry, so if you're doing this course and producing reports, you are very welcome to use any general purpose data analysis program. Can be MATLAB. However, for home use, if you want some open source software, and if you want software that is widely used by professional statisticians, then you might want R and RStudio. So here are some links on this slide to how you could get this. So you need to get the R software language itself from CRAN, the Comprehensive R Archive, probably network or something like that. So link to you. So there's the R software language. There's RStudio, which you will almost certainly need. That's a reasonably good, freely available graphical user interface for doing work in R. And I note that if you want to produce nice graphics, you will, within RStudio, almost certainly want to get hold of the ggplot2 package for producing good quality graphs. All of these are quite useful. Large numbers of tutorials are available on the internet for R, so I won't go through those in this course or in these videos. But I would recommend, if you do want to do data processing and producing graphs at home, semi-professionally or professionally, and if you want open source software, then R is a good way to do that. Just to show what it looks like, so that's RStudio. So you've got the usual expected console, feedback from the machine, some sort of explorer for your data, and a thing for visualizing graphs, and various different ways for you to save your graphs into formats that you can actually make use of. Plenty of tutorials available on the internet for how you would go about with this language producing graphs. This one is this one. I mean, the topic being looked at is the hilarious corruption perceptions index for various different countries against human development index. In other words, how nice is the country as a place to live. And this is just shown as an example of if you wanted to produce the pretty good quality graphics that you get in, say, something like The Economist magazine, you can produce that at home with your versions of R, which are readily available for you, open source. Not, by the way, that I highly recommend The Economist magazine. I do quite like their graphics and their figures. I'm not saying that I trust in any way any of the stuff that you find written in the essays, but they do have good graphics. Great. Right, now it should be fairly clear that graphical presentation of data, it can do a lot of work. It also, the correct choice of a good graphical presentation, there's an element of art in it. Let's just go back to the section 2.1 and briefly just review what are the key principles that we have to keep in mind when you're choosing a graphical representation of data. So I've got them written down as A, B, and C, as clarity, fidelity, and completeness. So you'll find, depending on what textbook or source you look up, you'll probably find terms like these, or these ones exactly, used to talk about what properties do you want from a graphical visualization of data in particular, or sometimes just from a numerical list of data or something. Now the thing is, these principles can be slightly conflicting, so sometimes there's a trade-off to be had between clarity and completeness, for example. Do you want to give a nice, clear, easy to understand graph, or do you want to list every numerical measurement to its last decimal place in a way that you can't necessarily show in a clear graph, but which you could in a list of numerical data? There's a trade-off between them. We'll have a couple of examples coming up of kinds of data where these things are important, but by clarity, I mean what you want to achieve is your display of your data should make the data understandable. Obviously, this includes your graphs need to be legible, correct sized fonts and things. Also, it means that your graphs should not be overcomplicated. You shouldn't have 20 categories of things when actually you could have binned your categories into only 3, say, that were fundamentally different. We talk about fidelity. What does that mean? So that means you need to, honestly, be honest about your data. That's part of being faithfully representing it in the visualizations, but also not just, you also have to be careful that you don't accidentally lose some important information that you recorded when you're making a visualization. We can have a look at what happens if you do accidentally lose some categorization that was important. We'll look at that in a future video when we talk about Simpson's paradox, or the inversion paradox. However, often for fidelity, just bear in mind that if you group or summarize data, you will lose some information about the exact observations that were made. So you need to make an intelligent artistic choice between grouping data, but not so much that you do too much binning of measurements that were actually distinct and shouldn't have been binned together. A difficult balance. It depends on the topic of what you're looking at. And completeness. You want to comprehensively display the data that you've got. Now, actually, life gets better for us here because we live in the 21st century. So, what traditionally is written up in textbooks as a trade-off between completeness and fidelity or clarity doesn't have to exist, because you may now have the ability to put up supporting data along with your dissertation or your paper. So, in fact, it's becoming mandatory for when you publish research results, you provide your supporting data in the form of the comprehensive, your complete numerical data in, say, something like an Excel spreadsheet that is properly titled and explained, at the same time as you provide a graph where you give a nice, clear representation of what you're doing. So let's look at a couple of examples of these trade-offs being used and somewhat intelligent choices being made. So, section 2.2, this shows a bar chart. What is it? Bar chart showing measurements of the viscosity of dimethylalanine, or whatever, some chemical or other. This is a perfectly reasonable representation. You see 3 measurements came out with a viscosity of 140 centipoise plus or minus a half centipoise, and then there were 3 other measurements. This does have clarity because it's pretty clear what's been observed from this bar chart. It doesn't have perfect completeness because what you would want to have that is a list of 6 numbers. Probably the numbers might have more numerical accuracy than plus or minus half a centipoise. So some of that has been lost to make a simple visualization. Anything else to say about bar charts? There are different names for bar charts. Basically, if the x-axis or the independent variable is continuous and your y-axis or your dependent variable is a count, then you have a special case called a histogram. Pretty much everything else, especially when the x-axis, so the different bars, are qualitative categories like cars, motorcycles, trucks, that will have to be called a bar chart, and in general you're looking at something called that. If you do have a histogram, you might have something like this. So, histogram showing weight in kilograms of 2 samples, brackets, male and female student volunteers, with some fancy partially transparent bars so you can see the overlap between the samples. These, being histograms, obviously big samples, tend to give you the probability distribution for the population they've been drawn from. At least they should do. But watch out here. Strictly speaking, this graph shows you the histogram of exactly what has been measured. When I just said, well, this tends towards a probability distribution for the population, be wary of all sorts of things which happen when we start to extrapolate using inference to the population about which we do not have absolute certainty. What could be going on here? Well, there could be some interesting sample bias coming on here. We'll talk more about that in later videos. But sample bias. This says in the caption, this is male and female student volunteers. So immediately you've got dangers that you could have if you extrapolated to a wider population. If you tried to extrapolate to the whole population of whichever university town these people have volunteered in, you'd probably make some mistakes. The average population would be older and most likely heavier than these students. Also, these are volunteers, so it doesn't tell you anything about the weight in kilograms of people who don't volunteer. And potentially there has been some oversimplification. I don't have any reason to believe there has, but you can imagine, well, if this survey had been done in an engineering department, then I imagine that your student volunteers are quite normal human beings, well representative of people of their age anyway. But maybe it's been done in a sports science faculty, where people might have anomalous weights. Certainly, probably they'd have a very different distribution from the general population, or from the general student population, if they were students where you've got sampling bias because of the type of student that you've asked to volunteer. So if that had been the case, then that's the sort of thing that you should have in your caption. Right. Section 2.3, scatterplots. Scatterplots are useful when you have information in two dimensions, or in other words, you've got measurements of some, you've got records about some things that you've measured, and for each thing you've got two numbers, each number being a continuous variable. In that case, scatterplots could work very well. You get something that looks like this figure 2.3a, but I've chosen this figure 2.3a because I've drawn this from the literature, and it shows an amusing property that happens, and why you need to watch out when you're reading your captions of things. So this is figure 2.3a. This is a scatter plot in which you've got a number of observations which seem to have a very good straight line relation. And the caption says, effectiveness, watch out for the word effectiveness, because you'll see why there isn't, effectiveness of the drug amiloride. In a study, 14 patients were treated for 2 6-month periods. In one period, they were treated with the drug amiloride using an inhaler, and in the other, they were treated with an inhaler containing none of the drug, brackets, a vehicle. Lung volume, that's called forced vital capacity, or how much air they can breathe in litres, was measured at the end of each period. The diagonal line shows where the measurements have equal value. It is not a best fit line calculated from the sample, and I've had to circle that in red because that is a horrific line, which it's correct. You need to know about it, and if you didn't have it circled in red, this would be dangerously easy to miss, because you might think that the diagonal line in the graph was a best fit line between the forced vital capacity, or how much air the patients could breathe on the x-axis before being treated with the drug, and on the y-axis after. And you might think, good straight line relation. You might you might go and interpret this as being straight line relation. This means the gradient of the relation gives us the effectiveness of the drug. Actually, no, this is a line to guide the eye with the relation 1 to 1. In other words, the straight diagonal line is the line where you would expect the observations to lie if the drug had exactly no effect and you had the same in your patient's lung capacity without the drug as with the drug. So keep your head about you when reading what is being described in your figure captions, because in this case the records are all very close to the diagonal line of lung capacity being exactly the same after treatment with the drug as before the drug. Danger, danger, danger. So do read captions very carefully. What's the next comment? Well, scatterplots. Scatterplots can show you numerical data in 2 dimensions. Dot plots effectively give you numerical information in 1 dimension, which you typically do for things in a few different categories. So question, could the dot plot data for the guinea pig tooth lengths under different drug treatments be more effectively or as effectively described with a scatterplot, which is apparently a sophisticated thing that can handle 2-dimensional information? Would the tooth length data by vitamin C dose be just as well represented on a scatterplot as by dot plots? Answer, probably not. As you can see from these graphs, if you do in the bottom graph give your guinea pig tooth length against dose, because the doses actually fall into 3 exactly chosen numbers, your scatterplot ends up with this not aesthetically very nice 3 splodges of vertical line values. It's correct, but it's a bit harder to see the dots. Certainly when some overlap, you can't see that there are several measurements of similar length for a particular dose. That is made clear that there are several measurements of the same length for a particular dose in the dot plot at the top, which is just a 1-dimensional measurement. And the fact that it's 1-dimensional is shown to you by the color code. But you have to watch out because the y-axis on the dot plot, you could accidentally read this as a continuous scale. The fact that it's a dot plot where the dose is a category, you need to interpret from the fact that you've got markers of different color, and they should really also be of distinct shape. Good. Right. We've said in this video some things about types of data visualization and the role of describing data within data analysis as a whole. We've talked about clarity, fidelity, and completeness, and we've not looked at the details of how to plot different graphs, which I'm sure you know or can easily find out from help files on the internet. But we've looked at examples of using these principles to show some data in some graphs. I think we'll save for video 3, looking at one of the hazards when you have perfectly correctly done data visualization. One of the dangers is overinterpretation. And this example is from Murray Gell-Mann's Bayesian data analysis book, so you can read all about it in much more detail and the exact statistics if you want to have a look through that weighty tome. But the basic question, and which illustrates the hazard of overinterpreting data, is something I'll show on these couple of slides. So overinterpretation. This is a map of the USA, and highlighted in black are some counties, and the counties shown are counties in the USA that have kidney cancer death rates in the highest 10% for a population that should be consistent. So this is for United States white males. Is for that county the mortality, the number of people dying per 100,000 population per year, is that in the highest 10% of all of the county values for the United States. You see there's a spread of where these counties are. These shown in black are high death rate counties. You can see there's some in the Midwest and some in the West, and very few on the coasts. And the question for next video is, why does that come about? And at the same time as why does that come about, here's the next graph showing something very similar, but this is the counties which have the kidney cancer death rate, age standardized for white males, in the lowest 10% of the values recorded for counties. And here again you see, well, there's some of these counties, there's some in the Midwest, quite a few in the West, and very few on the coasts. So how do these patterns come about? The important thing to say while you think about this is that these are descriptions of which counties have in the highest 10 percentiles or the lowest 10 percentiles kidney cancer death rates. There's no doubt that this data is true, but the danger I want to highlight is what interpretations can people draw from this, because you'll see it's very easy to overinterpret. We'll talk about that in the next video. You can think about it before then.